Hi everyone, please take your seat. Start again. So please find your seats. Thank you. Hi, so I would like to introduce our next speaker, Omer Shalev from Intel Advanced Analytics Department, who will present his work on leveraging the power of bagging in multiple instance classification. Thank you, Omer.
Okay, good morning. Thank you for joining this session. This is me paying my dues to Intel's Legal. And before we start, just a few words about Advanced Analytics, which is the department I am coming from. So in Advanced Analytics, we build software solutions which are based on AI, and we provide these solutions to various verticals at Intel. The first activity, for instance, named AI in products, is about putting AI inside the chips, inside the processors, in order to achieve improved power consumption and performance. We have other activities related to product development, manufacturing, sales. We are not Mobileye, but we do work on Mobileye data. We try to derive various insights from the cameras related to smart city and road management. The health activity focuses on clinical trials, and last but certainly not least, we try to put AI in the process of hardware validation. What we try to achieve is faster time to market of Intel's products, and we do that by empowering the bug finding process with AI. That is also the activity which I am part of, and this is where the use case that I will now present comes from. So bug prediction is a real use case that we worked on last year. It is a manifestation of multiple instance learning, which I will explain here. We used a special bagging method for this use case, and it's also a use case which was deployed in production for a real customer. And I want to start with the pain. And the pain is named debug. We have several studies showing that over 40% of the time of hardware engineers is spent on debug, as you can see, more than any other activity. And as I said, one of the goals in my team is to reduce this time. Now, the good news from data science perspective is that debug is a data-driven process. We have information about the configuration of a test which caused the failure. We have log files documenting the recent changes, the recent actions that the hardware was doing. We also have the source, Git, for instance, so we know what the recent changes in the code are. And also information about existing bugs, which might be related. And the debugger uses all these sources of information to analyze a failure of a test in order to reach the root cause. And in order to understand what bug prediction means, we first understand how the validation flow looks like. And it all starts with the developer, which does some code changes. Then there's this iterative process of unit tests, which might fail. The developer will immediately fix them. And once this is completed, the developer can submit his code. That is the simple part, the part I believe we're all familiar with. But in the development of hardware, like in many other complex systems, there's this additional testing phase at system level. And this results in multiple test failures and several bugs among them. Now, unlike the case of unit tests, here we can't simply assign these test failures to specific developers because these failures are the result of multiple code changes by multiple users, multiple developers. And that is where things are becoming more complicated. And it even turns out that at the validation teams at Intel, there are thousands of such test failures every week, which makes it almost intractable to debug all of them. So how do the validation teams at Intel deal with this huge amount of failures? Even long before AI came to the picture, they had this rule-based system, which is based on expert knowledge. And this system runs the set of rules on the failures, and it routes them to different groups of tests, which they call buckets. And these buckets should contain similar tests, which in each bucket should belong to the same root cause. Then each member of the debug team is assigned one bucket, and he or she doesn't have to go over the entire bucket, but instead they sample just one or two tests. And here comes the interesting part. It turns out that some of the buckets are real bugs. These can be either software, firmware, hardware issues, which are typically more important and more urgent for debugging. But others are not real bugs. These can be sometimes bad configuration of the test, or some problem with the testing environment, and so on. And the thing is that to be able to tell that, the debugger must complete the debug process. So as machine learning engineers, we understand that we can bring here value if we predict the resolution type of the bucket. And it is also pretty trivial that we have here a case of binary classification of buckets, in which positive means real bug and negative means not a bug. Now, in an ideal world, every real bucket contains only positive tests, and the same goes for the negatives. But I remind you that we have here a rule-based system, which doesn't always do its work flawlessly. And I also remind you that our debuggers don't debug each and every failure. They just sample one or at most two failures from a bucket. So what this means from data perspective is that we have heterogeneous buckets, as we can see here, meaning that positive real buckets can contain negative tests and vice versa. And at this point, I want to switch the context and tell you a bit about multiple instance classification. And I also wish to convince you why this use case that I just described indeed falls under this category. So we all know the setup of the traditional single instance classification, in which we have labeled data, positive and negative in the case of binary classification. And using this data, we train some classifiers such that given a new instance which we haven't seen before, we can predict if it's positive or negative. Now, in multiple instance classification, things are a bit different. We no longer have the labels at the level of specific instances, but instead, we're given groups of instances that are labeled together. As we can see here, we have two groups, the blue groups that are labeled positive, and three groups, the red ones, which are negative. And we still want to be able to use this data to train a classifier such that given a new instance, we can predict if it's positive or negative. And sometimes we're going to be asked about a new group, a new set of instances, if it is positive or negative. Now, this isn't a new concept at all. It was presented already in the early 1990s. The actual term multiple instance learning was introduced by Dietrich in 1997. And in order to understand how we come to solve this problem of multiple instance classification, we must look at the internals of each of the groups. Now, in an ideal situation, we will have homogeneous groups, as we can see here. Every positive group contains only positive instances, and the same goes for the negatives. But if that is indeed the case, we don't really need the multiple instance classification methods. We can use the traditional single instance methods. So the more interesting cases are the ones in which we have heterogeneous groups, as you can see here. The positive groups might contain negative instances and vice versa. But again, I remind you that we only have the information about the labels of the groups. We don't have information about the specific instances. But we understand that there must be some relation between the label of an instance and the label of the entire group, right? So we must make some assumption about that relation. And the standard assumption, which is taken by many among the existing algorithms, says the following thing. A positive group will contain at least one positive instance, which means that it can contain also negative ones. On the other hand, a negative group will contain only negative instances. And it is clear that this assumption is asymmetric. And I now want to show you an example for an applicable problem in which this asymmetric assumption indeed makes sense. So the work on drug activity prediction was presented in the work of Dietrich, which I already mentioned. And the goal is basically to predict the strength of binding of a certain molecule to a given desired protein. And this indicates good qualification for drug making. It is quite obvious that we have here a case of binary classification of molecules, in which positive means good qualification and strong binding, and negative means weak binding. Now, I don't have any background in chemistry, so perhaps I'm not using the precise terms, but molecules have different shapes. And these shapes, these different energy states, they bind differently with the desired protein. In this example, for instance, we see two shapes of one molecule, one which, the blue one, which does bind well and is therefore positive, and another one which doesn't. Now, the problem here is that in this data, we know for a molecule if it binds well or not, but we don't know which among its shapes is responsible for that. Again, it won't be a good idea to trust my knowledge in chemistry, so let's treat these molecules just as nice drawings, but the point here is that we see why the standard assumption, which I mentioned, makes sense. Because we have here on the right these three red groups of molecules, which we know that don't bind well. And on the left, we have the two blue molecules, which we know that they are positive. We know that at least one of their shapes is strongly binding with that protein, but we don't know which among them is responsible for that. And again, we want to use this data to train a classifier such that given a new molecule, we can predict if it's positive or negative. And here we see why the standard assumption indeed makes sense. If you go back to the various types of test failures in hardware validation, our goal is basically to predict for a bucket, for a group of tests, if it's real or not. This has implications for priorities for the debug teams. And as I said, the labels that we have are at the level of buckets, not single tests, not single instances. But we do know that some of the buckets might be non-homogeneous. In other words, if that is the data that we have, we want to train a classifier such that given a new bucket, which we haven't seen, we can predict if it's likely to be positive, meaning real, or negative. And that is exactly the setup of multiple instance classification that we are discussing here. Now, can we use any of the common existing approaches in multiple instance classification for bug prediction? There are two families of algorithm. What embedding-based approaches do is they take each group and they convert its content to a single data point in an embedded space. How they do that, that depends on the specific embedding method, but once we are in the embedded method, we can use any traditional single instance classification algorithm. Instance-based approaches, on the other hand, that's the other family, they work at the level of existing instances. They try to find the most representative ones, and they build the classifier on them. Now, unlike the case of embedding methods, here we can't use any generic classification algorithm because we are dependent on some assumption about the distribution of the data, typically the standard assumption that we have previously seen. And therefore, we can't use any generic method, but the methods must be tailor-made. Can we use embedding-based approaches for bug prediction? The thing is that in our case, we have only a few dozens of buckets, which is quite a lot for the debuggers, but not that much for training a classification model. Can we use instance-based approaches? So as I said, to be able to use them, we must be compliant with some assumption. And the standard assumption that we mentioned says that negative, here the red groups, the red buckets, must contain only negative tests. And that is not the case in bug prediction. So we don't have here an asymmetric case, and therefore we can't use the common approaches for our case. So what did we do? Here's the approach that we took. There's an additional challenge which I didn't mention up to this point, which was also the inspiration for the solution, and that is the disparity in bucket sizes. We can have several buckets which can contain hundreds or thousands of tests, but on the other hand, some buckets can contain as few as 1 or 2 tests only. Now, imbalanced data is always a challenge in machine learning, and specifically here, if the big buckets get too much weight in the model, then it is prone to be biased to describe the big bucket instead of the entire resolution type. But a very common solution to imbalanced data is bagging. And what bagging means in its simplest form in single instance shape is that we sample the data, we train one classifier, we then sample the data again and train another classifier. We repeat this n times to generate an ensemble of n classifiers, such that given a new instance, we can predict, we can query each of the classifiers to see if it's likely to be positive or negative. So we tried that on our data, and it was not a surprise that we got biased classifiers, which more emphasized the big buckets, as you can see here, and failed to predict even on the trained set, as you can see here. So what did we do? We decided to go for a very simple approach which leverages the knowledge of the groups, of the buckets. And we have here a two-stage bagging algorithm which does the following thing. First, we select k groups, k buckets in our case. Then among the selected buckets, we sample the instances. On this data, we train the model. This is, of course, repeated n times so that we eventually get an ensemble of n classifiers. And now for the inference part. There is a new bucket with new tests, which we haven't seen before. What we do is we query the ensemble model. On each of the tests, we get their scores from the ensemble model, but the decision has to be made for the entire bucket. And here we decided to take the median, because as I mentioned already a couple of times, our buckets are heterogeneous. And the median, what it does is emphasize the label of the majority and neglects the effect of outliers. But again, the train data is also heterogeneous, but there's an additional benefit of bagging, and that is the fact that it emphasizes the majority and neglects the effect of outliers. So that was the approach. Now I'll tell you a bit about the results. So the first thing I want to show you is a comparison we did against common approaches on a public data set. That's the mask data set used by the work of Dietrich, the molecules. There are here 92 groups, in total 476 instances, and 166 continuous features. And we chose four, here, right to the line, four common approaches in multiple instance classification, which are all variants of SVM. For our multiple instance bagging, we also used SVM as the base model. We didn't do much of hyperparameter tuning here. We just wanted to get a feeling. And we did a comparison in terms of precision and recall, as you can see here. And what we can conclude from this graph is that our approach is at least competitive with the other common SVM algorithms. We also wanted to take a deeper look at the multiple instance bagging versus single instance bagging, which is the traditional bagging. And here you see the precision recall curve depending on the threshold parameter. And it is quite clear that the area under the blue curve representing multiple instance bagging is larger. Now, as for the bucket data, the real data that we had, we reached average precision of 80% and average recall of 50%. This was quite a significant improvement compared with 70% precision and only 35% recall, which we had using the single instance bagging. These results were also quite satisfying for the needs of our customers. So now to wrap up things. So I brought here today a real use case of a real problem which was deployed in production. I tried to convince you that this is indeed a case of multiple instance classification in which the labels are at the level of groups, not instances. I also showed you that the existing approaches in multiple instance classification don't match here, and therefore we had to go for a special bagging approach, which is the two-stage bagging that I showed. And finally, we've seen some results showing that we are at least competitive with common approaches. That was my talk. If you are interested to hear more about what we're doing at Intel's IT, feel free to visit the website. Thank you very much.
Thank you, Omer. Do you have any questions for the speaker? Yeah. Exercise for the day.
Thank you. You said that by definition, if you have one sample of one instance of positive in your bucket, so the whole bucket becomes positive, right?
Can you hear me?
Yeah.
I didn't say that.
Okay, so never mind.
Any other questions? Clarifications? No? So let's thank the speaker again.